just to get a feeling for the audience, so who is familiar with Markov state models? So who has built a Markov state model before going to this workshop? Let's see, like one. Okay. So now who is familiar with free energy calculations? So who has done free energy calculations? Okay. Also very small fraction. So who has done already both free energy calculations and Markov state modeling? Oh, quite a bit. Okay. So I guess you will profit right the most because we will show you how to combine these two things. But even for those people who have only done one or the other, it will be interesting because the methods we are going to present today, they work also can be also used just for enhancing Markov state models or enhancing free energy calculations. So even like if you don't plan to combine the things in your own work, it's even useful to use them together with Markov state models or together with your free energy calculations. And for all the others, right, who are new to this field, I mean, these are the ones which will be not bored during the first half of the talk, where I will talk about the enhanced sampling method. So enhanced sampling is a very old discipline, so it has been around like for many, many years. I don't know, 50 years, like since the invention of the computer and Monte Carlo simulation, people thought about how to make this faster and try to come up with some tricks. And of course the field is evolving, and with, in a sense, like combining Markov state models and free energy calculations is like something like a new step, a new methodology in the field, which might or might not become very important for your future as a researcher. I mean, it depends how well, right, we convince everybody else that this is important. But it's a kind of a new approach to free energy calculations, which you could be interested in knowing about before it becomes mainstream. So let's start. Multi-ensemble, Markov models, and WHAM. WHAM is the estimator which does the trick. It's the name for the estimator. So let's show you briefly the outline. The first part of the talk is about free energy and free energy calculation, and the simulation types that you can carry out to do this so-called free energy calculation. There's Boltzmann reweighting, and then I'm going to focus on umbrella sampling, on multi-temperature simulation, and talk a little bit about the details and the underlying assumptions about these methods. And for the rest of the talk, I will focus on analysis methods. So like this is like something like the input data, like the goal is the free energy calculation and simulation type of the simulation with the data that you have, and then you have to analyze this data. There's multiple ideas around how to analyze this. So like this is a typical one, which maybe most of you might be familiar with, weighted histogram analysis method. But it's a very simple idea, but for this reason it also carries a lot of problems. And this will also work as a way of introducing better estimators like WHAM with Markov state models. And then there's a distinction between bin version and discrete version, which you will see during the talk. So let's start with free energies. So what are free energies, right? If you don't have, if you type this into Google, right, and if you look on Wikipedia, you get like two answers. Like one of them is a esoteric concept of free energy, like that you can build like a perpetuum mobile. Like that's not the definition of free energy that we are going to use in this talk. In this talk, free energy is a probability, or it's proportional to minus the logarithm of probability. So that's the definition. So of course there's a thermodynamic concept of free energy, and it has a certain relation to temperature. But for the sake of this talk, you can think of this as something as like the logarithm of probability. So, and there's like two categories how this term is used in molecular systems. If people talk about free energy, so I call this A and B, and so category A, this is things that you probably have seen during the talk. You calculate a stationary distribution from a Markov state model. So you define a certain set of states or macro state. For example, for this protein ligand system, you draw a shell around the protein, and you say if the ligand, the small molecule, is inside the shell, you define this as bound, right? So you define two states, bound and unbound, and then you ask for the probability that the ligand is inside the shell. So it's the probability of the bound state. This can be formulated more mathematically, right? As an integral over an indicator function, and this integral is it's a stationary probability, and from chemistry we know that this can be calculated as an integral over the Boltzmann distribution. So right, the integrate over the Boltzmann distribution is an indicator function of the bound state. So you get a probability to be bound, and if you take like minus logarithm of this, you can say this is like the energy of binding. This would be definition A, or use A of the term free energy. There's something else slightly related to this definition, and here it's a definition. The definition of free energy is the ratio of partition functions of different thermodynamic states. So what are thermodynamic states? These are, for example, like two different temperatures, like 300 Kelvin and 350 Kelvin. So each thermodynamic state has its own Boltzmann distribution. Parameter beta changes in the Boltzmann distribution. So you can calculate for every Boltzmann distribution, you can calculate like the normalization constant, which is called the partition function in chemistry. And if you have two ensembles, for example, two temperatures, the ratio between these two normalization constants is also called it's the exponential of the difference in free energy. So this is like a concept which is important, arises in many places of chemistry and physics. For example, if you want to calculate entropy, one of the Maxwell relations is S equals minus partial derivative of free energy with respect to the temperature. So if you would do this numerically, right, you would probably express like this derivative as a different quotient. So it would take F1 minus F2 divided by T1 minus T2, right? And this difference in free energies of two different temperatures is exactly this term, right? It is here in the exponent. So that's the use of this ratio of partition functions in chemistry, for example, calculating entropy. Instead of calculating probability to be bound according to this definition, you can also do it in a different way. And it's usually done in these kind of thermodynamic cycles, where you don't have two temperatures here, so you don't have two Boltzmann distribution corresponding to temperatures, but they correspond to different interaction states of the ligand and the protein. So you use like one of the Boltzmann distribution would just simply correspond to your physical system, like the one you would simulate here. And then you introduce a second Boltzmann distribution where the energy is changed, such that the interaction between the ligand and the protein is zero, or it's tuned down. And of course, right in this ensemble, like they won't bind, they will dissociate these molecules. And there are certain tricks that you can do. I'm not going to go into the detail here, but from like calculating such ratios of partition functions between the physical ensemble and the bias ensemble, you also can calculate the probability to be bound. So these are the two uses. So in this tutorial about rewriting methods and WHAM, both ways of describing free energies are covered. So both quantity can be calculated from the methods which I'm going to present, or Chris and me are going to present during this last day of the workshop. Okay, as an important note, because it's a question which has come up in the last years. So if you just want to do like this kind of simulation, where you just do simulate in one ensemble with one Boltzmann distribution, one temperature, you can in principle do this without all the free energy stuff, right? Because if you're just asking for a probability that certain events are happening, you can just go on and simulate and calculate this quantity from just a very stupid normal MSM without doing any rewriting. However, like practically achieving this, it's very technically complicated to sample this distribution. So like there's also additive sampling methods which can be used together with the MSM. So in principle, this definition of free energy you can get from a normal MSM. Definition B, no chance, right? Here the definition includes that you simulate two different thermodynamic states. So this will require some kind of rewriting technique. Okay, so now the question is, why should we do like this rewriting, this important sampling? So as I said in the beginning, like since like the computer was invented, people tried to sample complicated distributions, for example, of molecules, of some materials on the computer, and they quickly like run into the problem of beta stability, right? So if you have like an energy landscape which looks like this, so it has a very deep minimum and maybe like a second less shallow minimum, but one that you're still interested in, like running all these simulations and waiting for them to overcome the barrier. This can take a very long time. And most of you who have worked with molecular systems, they know that you never have enough simulation, right? So even if you simulate like a millisecond, it's never enough, because there's always one more barrier or something which needs to be explored, something interesting which you have not yet seen in the system. So the question is, how can this be made easier, right? How can you finish your project on time? So in the case of stationary observables, so I'm not talking here about kinetics, but just like stuff which is independent of time. There's a trick that you can do. It's a very simple trick. Is to change the energy landscape that you're sampling from. So as it goes as follows. So say you have your expectation values that you want to calculate. Let's call this quantity O, and index 0 stands for the ensemble. Could be like the number of your temperature, for example, a temperature number 0, right? For example, 300 Kelvin. So it's defined as an integral of the observable function O of x integrated over all conformational space and weighted with the Boltzmann distribution. So in practice, right, you don't do this integral analytically. You can never do it analytically for large systems. What you sample, you approximate this integral by samples of O, of the function O evaluated at the samples. And the samples, they have to be picked according to a special rule, right? So these samples, xn, they have to be realizations drawn from the Boltzmann distribution. And that's something which the MD simulation, for example, does for you, right? So if you would sample uniformly from your MD simulation that has run for a long time, this would be distributed according to the Boltzmann distribution. So this x is your simulation data. So now we can do a trick on integrals such as this by multiplying it with 1. So if you see like this factor, e to the minus beta u1 of x plus beta f1, I've added it in here and here below, down below here. So it cancels effectively, right? So I now can rewrite this equation a little bit, just put the exponents together. And now I'm insert the approximation. So I'm not doing the integral. So this is an integral that I could in principle do analytically if I could do it, right? But as there's a problem with sampling, I have to approximate this integral also by a sampling procedure. So again, I have to collect samples xn, and they have to be collected by from a certain distribution, namely this distribution, right? So as a trick, right? So this integral I was sampling, I had to draw my frames from the distribution with the index 0, and now I can draw them from the distribution with the index 1. So I can sample my frames from a different distribution, but what I have to do, I have to include this additional reweighting factor, right? So if I would do like this very simple simulation, I didn't have to include any reweighting factor, but now because I've added this 1 and I've changed the distribution I'm sampling from, every sample x1 has to enter the sum with a rewriting factor. So that's the trick how you can change your energy landscape. And this is an identity, right? It's O of 0, O of 0. So in the end, I'm getting the same expectation value, even though I've changed the energy landscapes that I'm sampling from. At the price that I have to use a rewriting factor for every frame. But in principle, that's not a problem, because these rewriting factors can be calculated from the MD software. So let's define a few technical terms, also to make the notation a bit simpler. So there's like many symbols which enter this equation. So beta, right? It's a permanent beta 1 over K Boltzmann T temperature. U is the energy. These are free energies, right? So these are normalization constants in some sense of this probability distribution. So let's define like the bias energy. The bias energy is a term which occurs in this rewriting factor here in the first two exponents. So let's call like the difference between the energy 0 and the energy 1 the bias energy. So just to go back to this very simple example, let's assume that this was your original energy landscape, and your goal was like to sample this transition as quick as possible. I mean, not the transition, but some stationary expectation value, which is influenced by values in both minima. So very simple trick would be to flatten this energy landscape completely, right? So now by this trick, I have the choice to change my energy landscape in any way that I want, right? In principle, I can choose this factor. So why not be very bold and make this energy landscape completely flat? So this would be for simple systems would be the optimal choice, right? So here there's no metastability left at all. The system will quickly diffuse along the x coordinate. So how will this be achieved, right? So what I want is that my energy 1 is 0, and of course U0 would be like the physical energy, and so it means I know how to select the bias, right? So for the optimal bias for this very stupid system would be to select it as minus the physical energy, right? You take the physical energy, add to this minus the physical energy, you get a very completely flat system. So this would be the thing. This would be the solution. So if all molecules would live like in a one-dimensional space, we would be done now, and everybody could go home. But like life is not as simple. So there's like many more dimensions than one. Usually like hundreds to 10,000 of dimensions, or like even billions of dimensions in large molecules. Like three per atom, right, or 6 per atom if you include velocities. So we have to think more carefully how these concepts would work in a high-dimensional space. And some concepts that people have come up very early with is the concept of an order parameter. So let's say now that we have a more complicated system. So on the last slide we were in 1D, now we're in a high-dimensional space, 2 dimensions. For visualization purposes, but it starts even to get interesting in 2 dimensions. So how would you sample from this distribution? I mean, making it flat becomes a bit of a problem. I mean, if you would draw uniformly from this distribution, maybe it's not such a good idea, especially in high dimensions. So drawing uniformly means also that you draw a lot of frames from the corners here, right? Which have 0 probability actually of being, or a very small probability of being visited by the physical system. Well, of course, this is even more dramatic if you go to higher dimensions. So if you just pick sampling uniformly means picking a random conformation of the atoms. So random conformation of the atoms doesn't necessarily constitute a molecule, right? You just shuffle your atom coordinates, like the bond length and all the dihedrals, and they will not form a molecule, right? So sampling uniformly in a high-dimensional space is impossible, so to say, because they are localized minima, and if you sample uniformly, you will always miss them. So what people have come up with is like to look into the system at hand. Like just not start very like with a blank page or blank slate, but to learn something, try to look at interesting states, right? So for example, here there's two minima, and to define something which is called an order parameter or reaction coordinate. So an order parameter or reaction coordinate is a coordinate. So it's like in a coordinate system in axis, right? Maybe here it has value 0 and then it goes on to positive values. And it's defined in such a way that it connects to interesting states. Interesting states could be like conformations of a molecule, could be like bound and unbound state, right? This could be like bound, could be unbound, for example. And one has to choose this in a clever way, right? So then you can calculate the probability along this new order parameter. So now you have made your high-dimensional system into a low-dimensional system. And we can now look at the projection of this high-dimensional system on the order parameter. For example, we can calculate like the probability to be in a certain location along the reaction coordinate. So what you're doing, right? You're projecting to the order parameter, which means all the probability. If you pick a certain point on the order parameter, and then you collect all the probability which is orthogonal to this point. Right? For this point, you collect all the probabilities along this line, right? You go like this, sum up along this direction, and this you call the probability of this. It's called probability at the location of the order parameter. So this is a mathematical form of writing this up. So you again do an expectation of the Boltzmann distribution, and for a specific value of this order parameter psi, collect all the orthogonal space, like which gives the same, which has like where the order parameter has this value psi, and you get something like this, like a one-dimensional projection of this energy landscape along the order parameter. So let's go back to the thought from the last slide, right? So what would be the optimal way of sampling this? Of sampling such an energy landscape would be to make it flat, right? I mean, if you wanted to sample uniformly from bound to unbound or from one conformation to the other, and have now made a choice that I now want to see my dynamics or my expectation values in this low-dimensional 1D space. The obvious thing which comes to mind is to try to make this flat, to find a bias which makes this energy landscape flat. So how would we do this? Right, we have said the optimal bias would be minus the PMF. This would be minus. So in this case, it was minus the energy of the original system. In this case, right, we have to take minus this value, which is the logarithm of this integral. It's called the potential of mean force. And there you have a problem, right? So if you try to insert all these mathematical objects into each other, so you know, okay, the optimal bias would be the one, which is a logarithm of this integral, right? You have to solve this integral. So somehow this doesn't bring you any further, this idea. So because like this integral is respect to the original system. It's like it's a property of the physical system, and that's just the integral that we cannot do because it's too complicated. Because like sampling over this barrier will just take too long. So like flattening the energy landscape is this very simple idea of picking minus like the logarithm of this probability distribution doesn't work in this very naive way. So let's relax this idea a little bit and say, okay, we cannot make it completely flat, but let's try to make it approximately flat, right? Maybe that's enough. You don't have to be perfect in this sense. And that's the idea behind umbrella sampling, actually. So what you do in umbrella sampling, you want to achieve approximately flat sampling. You want to create an approximately flat energy landscape from original energy landscape. And you here do it not by adding like many potentials. at a given time one potential. So instead of defining one bias energy, which makes the energy landscape completely flat, you introduce a series of potentials, like the red one, the blue one, which is in the middle, the green one, and then the blue one, which is more to the right. And like if you take them all together, somehow you can sample all the parts along this coordinate, right? So here you're sampling more on the left well, here you're sampling the barrier, and here you're sampling like part of the barrier and the right well. So you define just like many, you define many bias potentials. So it's, and you give them an index k. So here you see like this index can stand for different things. Like on the first slide I said it was like different temperatures, but it could also be like different umbrella potentials. So what we call the bias potential would be the sum of the physical potential and the bias that you add on top would be bias potential. Umbrella sampling is usually a typical form, so there's a quadratic form of the bias potential, but this has no special meaning. When you, in principle, you could choose any function in the form. It has to be quadratic. It doesn't have to be quadratic. And from this, I mean, in 1D, it's quite easy to calculate the probability distribution, which comes out if you insert this into the Boltzmann distribution, right? You put this energy into the exponent of the Boltzmann distribution, multiply it by inverse temperature, get the corresponding probability distribution, which looks like this. And as expected, right, there's like parts, like it's becoming approximately flat in the transition region. A second idea to achieve this flat sampling from an energy landscape is multi-temperature simulation. And it's even more simple, just change the temperature. So what you do is, so let's maybe start with this picture. So instead of simulating a temperature 0, you switch the temperature to a different temperature, beta k, and you remove like the all temperature by dividing by it, right? So you can call this like an effective bias potential. And how do they look? Oh, sorry. Well, they just become approximately flat, right? For higher temperatures, like the system explores more evenly all the phase space. So it's also a way of flattening the energy distribution. Okay. So this would be, one could like define something like a bias potential even for multi-temperature simulation by playing around with the equations. And this would be the corresponding Boltzmann distribution which shows the same behavior, but it's just more even at a high temperature. Okay. So of course there's like a small mistake with this picture. Like the truth is not so easy, because if you do a multi-temperature simulation, the system can also change dramatically, right? It's not even as simple as that, so the energy landscape becomes flat, especially if you're looking at a certain projection. So what could, for example, happen if you have a system, for example, if you want to study conformational change, and then you heat your system to like 1000 Kelvin. So what would happen is to your molecule, it would probably unfold and become a chain, like a random chain. When the water would evaporate and so on. So one always has to keep in mind this idea of multi-temperature simulation combined with a 1D projection is an approximate concept. So you should not, if you do a multi-temperature simulation, the system should not change dramatically. In the sense that the order parameters that you picked initially should still be a valid description which connects somehow the minimum. For umbrella sampling, this is more easier, right? Because it's very tied to the correction coordinates that you have defined in advance. Okay, so should I talk a bit about replica exchange? Okay. So that's like a second slide, which maybe might be confusing for all the people who have never worked on the topic. But might be very relevant for people who already know a little bit about free energy calculations to raise a bit the awareness about the problems, about the typical problems that you get in free energy calculations. And one very interesting technology, which I'm going to introduce very briefly on the slide, is called Replica exchange. And it's a way of working with multiple simulations simultaneously and achieving equilibrium, sampling from an equilibrium distribution. Or it's like a computational trick that you can do. So say you have like these two kinds of oh, the pointer is not working anymore, so I have to. Do you have a second pointer?
We have batteries.
Okay. It's even better. I'll just point with my hands. So it works. Whatever. Is it? Oh, doch. Okay. So say you have like defined your two biased, you have a physical double wave system, and then you have to find a second potential where the barrier is reduced. So what you do now, instead of doing the simulations sequentially, you run them in parallel. So you do an MD simulation or Monte Carlo simulation, and you simulate your original system, and you simulate your bias system, and at a certain point of time, you swap the conformations, right? So you take the x value that you found, that you arrived at the end of the bias simulation, and the x value of the coordinates that you arrived at the end of the physical simulation, and you swap them, just put them in the other ensemble. And to do this exchange, you do it with a certain rule, which I will explain in a minute. And the idea is, right, that like crossing barriers in this system is easier, and here it's complicated. And if you now do the swapping move, where you exchange the conformations, will achieve that like this barrier is somehow crossed even in the physical ensemble, but by this unphysical move. So these moves are executed with a certain probability, and they're not always accepted. What could also happen that a certain exchange move that it's tried, but it's rejected. So now let me give you the rule for the acceptance of this move. Oh, it's not working anymore. So this rule is constructed as follows: that we say that the whole simulation should sample from the Boltzmann distribution. And the Boltzmann distribution of a single system, this is very clear, right? It's e to the minus beta u divided by the normalization constant. So that's the Boltzmann distribution of a single system. And now if you look at a multitude of systems which are run in parallel, you could say that the distributions that I want to sample is just a product of Boltzmann distributions. So it's like independent systems, and every system should sample from its own distribution. So system 1 should sample from the distribution of system 0 should sample from the distribution of system 0, system 1 of the Boltzmann distribution of system 1. And now the joint probability of observing a whole set of simulation in a certain conformation is just a product of the Boltzmann distributions. That's how it's constructed. And if you have a stationary distribution, you can construct from the stationary distribution a so-called metropolis Monte Carlo exchange move. That's a way of defining the probability transition rates for this move such that this distribution is conserved. There's a general recipe of doing this, of constructing such a metropolis criterion based on a stationary distribution, which is used here in this case. I'm not going to talk about details, how this is constructed, but that's typical. You can just find it in any book about Metropolis Monte Carlo. That's typically Metropolis Monte Carlo. So this move now ensures that every system is in its achieves samples from the Boltzmann distribution, even though you arrived here at a spoiler crossing by doing something unphysical. And that's somehow also the general framework of TRUM and all these methods, what I'm going to present here. So we're going to do some unphysical tricks on the system and try to recover the kinetics from this. So what is here, what can be learned in addition from this system, or from this simulation type, is that these moves have to be accepted. It could also be that this move would always be rejected, and then we have a problem. And this points us at a deeper problem with free energy calculations. That one always has to keep in mind. And this is the overlap of the bias distribution, or in general, the overlap about distributions. So let's say, in this example, right, you do an umbrella sampling along the x-coordinate, and to accelerate this, so the physical distribution is 0 in this case, and you want to sample uniformly from the x-coordinate and you introduce like two umbrella potentials, like this dashed potential here on the left and this dashed potential from the right. And the corresponding probability distributions, they would of course peaked around the locations where the potential is larger than 0. And of course, right, if you would sample in such a way, you could not make any statement about the transition region, about the middle regions of X, and you would never have a global picture of the X coordinate, right? So if like the energy, in this case, the energy landscape would be flat on the right, the chart. So say your energy landscape, the physical energy landscape would have a step, and then you would sample from here, and you sample here, and you get frames from here, and frames from here. You would never see the step, right? So you would never know that this energy landscape contains a step. And the general thing that can be learned from all these observations is that such a kind of sampling, in principle, you could set it up, you could define these umbrella potentials, but the analysis of the simulation will give you nothing usual, nothing useful, right? So it's like this would be like I mean, you could run the simulation, but you would learn nothing from it, and you would realize this only at the stage of the analysis. So that's an important thing to keep in mind. That you should have overlap, so that you should have like conformations which are sampled, or that you sample the same conformation or similar conformations in the bias distributions. And that's achieved usually in umbrella sampling by adding more umbrella potentials. So we add another one here, right? And maybe another one here. And then you're going to start to have overlap. So then you're getting a global picture of what is happening along the reaction coordinate. So there's a certain way of diagnosing this. And it turns out, if you have such a situation like this, where you have bias potentials which don't overlap, if you would run this in this replica exchange setting, you would never get exchanges. So let's look a bit more in detail about the rule for this exchange acceptance probability. Look at the terms that they contain. So it's in principle it's like two exponents or 4 exponents. I mean, you could like rearrange the terms such that they are into 2 exponents or one big exponent, and it contains certain energy difference. So here it's the energy difference between energy 1 and energy 2 of the conformations x2 and x1. And what is this? I mean, I can tell you what this energy is. It's telling you. It's somehow something like the gain or the loss in energy that you get when you exchange the conformations. So this conformation, right, like this red ball being on the left side and this blue ball being on the right side has a certain energy. And then you can ask for the energy that you would get if you would accept, right, this move. Or if you would compare the energy of this conformation, we have exchanged the conformations by the energy of the original conformations. And this term is, this energy difference is like included in this, as written in this exponents. So principally you're accepting by the gain or by the loss of energy that the exchange move gives you. So now if like you're in a situation like this, right, you're here on top of the barrier, and if you would now swap conformations, it means you would take this value where the particle is located on the middle of the barrier and put it here on this much higher barrier, you would have a huge loss in energy, right? It would require a very large amount of energy to put this particle on this higher barrier. So that's why this move is rejected. And the same can be said about an exchange between like non-overlapping umbrellas, right? So say you take like a blue sample and you try to evaluate the orange energy at the blue sample, right? So we would ask, okay, this sample, this blue sample, what's the corresponding orange energy, right? It's extremely large, right? Even if you take this sample, try to go up and look where's this parabola, at which location the parabola would go to this side, right? So I would have to go all the way up to find the value of the energy, right, of this blue sample. So this blue sample has an extremely high value in energy in the orange potential. This means carried out in a replica exchange fashion, exchanges would always be rejected. And so that's a way of quantifying overlap between distributions and to make sure that your sampling actually covers the whole order parameter. So we can check as a way of checking overlap. We can just do this very simple idea. So no matter how you simulate it, if you simulate it with replica exchange or not, just ask the question if the sample would have been generated by replica exchange, how many would have been accepted? And this gives you a value of overlap. And just a way of, so it's like a score we define. So you ask if I would have run this in replica exchange fashion, how many exchanges would have been accepted, and this should be at least like larger than 1. So this value, there should be at least like 1 exchange which should have been accepted. There's also different ways of qualifying the overlap, but I like this form very much because it's so simple. Because all these values, you can just get them from the MD software. So it's very simplified. So this is like was a word of warning very early on in this talk, but it's extremely important actually, because there's so much stupid, bullshit would be a hard word for the stuff which is published. But there's a lot of things which is published which is, I think is not quite right. That people don't pay enough attention to these questions. So let's prepare like for the second part of the talk, and let's try to make the notation a bit simpler. Because I'm quite tired of carrying all these symbols, all the betas and U and F and so on. I guess you're tired as well of looking at all these large expressions. So let's introduce a few symbols to make this shorter. So we have like here this weighted energy difference, like temperature at ensemble K times bias energy. So minus the thing plus the same thing at a different ensemble. Let's just give this a more simple symbol B of K, right? So the energy difference, we'll call this bias, but here now it's multiplied by different temperatures, so we just call this a dimensionless bias, just a symbol to represent the difference. And we make a specific choice, so we pick like ensemble 0 as a reference ensemble. So we always every kind of energy, we are expressing it as a difference with respect to the physical energy. So every, right, if you write it in such a way, you could say I fixed this as my reference of energy, as my zero of energy, and I express everything with respect to number 0. So that's how we get rid of this term. And then now we want to get rid of like one of these f's. And we also assume that the reference energy, the reference ensemble is shifted such that its Boltzmann distribution is normalized. I mean, as you know, right, in classical physics, there's no zero of energy. So we can just add a constant to every energy term, and that doesn't change anything physically. So we can just change the energies such that this term becomes 0, right? So this is like, so this was like the Boltzmann distribution, right? So we could, if we can add in a constant term to the energy, we can also add a constant term to the free energy, right? It doesn't make any difference where you put the extra constant. So to make life easier, let's assume that we have added a constant such that this term is 0. And let's also, to get rid of the last beta, let's introduce a log partition function, how I call it, a small f, and we just define it as beta of k times f of k, right? So then we can compress all these long expressions to this more simple form. And I will stay with this simple form for the rest of the talk. Should just keep in mind, right, that all energies are expressed with respect to the reference ensemble, and the free energy of the reference ensemble is defined to be 0. Okay. So with this notation, we are ready to jump into the second part of the talk, which is analysis methods. So say now you've done your simulations, you've defined your order parameter, or you have picked your temperatures, you have made sure that your distributions overlap, you have run the simulations, and now you get all these samples. Like you have for every, you've got all these data points that come out from your MD simulation. So now it's time to analyze the data, and for this you can use some analysis methods. And the most familiar one will be, I guess it's WHAM, weighted histogram analysis method. And it works as follows. So we have, this is a picture from the theory section, right? These are like the probability functions which will correspond to the different biased energy landscape. We have added the umbrellas to sample uniformly from the barriers and from the wells. But of course this is theory, right? So you don't get this in your data. So what you get are realizations. This is the theoretical probability distributions. But what you really get is something like this, what you can get from the data. It's a histogram. So you get MD frames, and you can, for example, like introduce bins and put these samples into bins to recover a histogram which looks somehow like, right, the theoretical probability distribution. So now we've switched from probability distributions to realizations by carrying out the MD simulation. And like structurally, it's completely similar, right? Like for every bias that you've added, you get one histogram. So if you have, for the umbrella that you have added to the left, in the red ensemble, you get a histogram, or you get samples, however you call it. For the middle one, which samples the region, you get a green histogram. It's also realizations of the simulation which sample the transition region. And the same for like for the simulation which samples the right well. Also get a histogram. So now, in principle, you're not interested in the histogram, right? But the question that you set out to answer was, what's the probability to be in a given state? So now the question becomes how to relate these histograms, and especially the histograms from the biased simulation, back to a question about probability in the original physical system. And WHAM is a way of doing this. So it's a very simple mathematical model that you do, and has like 2 to 3 ingredients, however you would call this. So what you can introduce here is PyIK. And that's the probability of sampling from a bin number I. So I would be now an index along this discretized axis, and K is the ensemble, right? So these are the colors, red, green, blue. And you ask for the combination for the probability of a given bin position at a given ensemble. And there's something that we already know about this. That's why we can write an equation for it. And we know that K is a biased energy landscape. And we know that we have constructed this biased energy landscape by adding a bias to the physical energy. So we know that this probability of seeing a certain bin in a biased ensemble is equal to the probability of seeing this bin in the physical ensemble times the bias factor. That's just like the bias energy, right? And of course, we have to normalize by a certain way. So actually, that's a conditional probability of observing bin I given that you're an ensemble number K. So you normalize by the probability of being ensemble number K, so to say. So Z of K is just like a normalization constant, that's it. And then you construct, with this knowledge, you can construct a likelihood function. I mean, the likelihood function, I guess you have seen it for Markov state models. I guess Simon has explained this in his talk. I mean, who remembers seeing maximum likelihood or likelihood? Okay, so maybe I will explain it again then, just to make sure that everyone is on the same page. So maximum likelihood estimation is a way of relating a probabilistic model to data in different ways. Like, I think Jan-Henrik, you have explained it as well, right? But only on one slide.
The connection was that you want to have the most likely Markov state model, so writing down a function that depends on lots of variables, and then you try to figure out which numbers of these variables will give you the most likely model.
Yeah. I mean, just write down your equations again, right? So the graph can write down the probability of having a model, the joint probability of model and data, right? So you can write this down as a probability, just using Bayes' theorem. The idea is very simple, right? So you write down the joint probability of having data in the model in the Bayesian sense, and you write this out as conditional probabilities and rearrange it, and then you get the probability of a model given that you have observed a certain data. And this identity you can express this with, as this expression of the probability of drawing the data from a model. And then, so this is like, in the Bayesian sense, this gives you somehow it's the probability of the model, which is interpreted in the Bayesian sense as a degree of belief in the model. So you say, if this number is large for your model, it's a good model. It's a very probable model given your data. So the maximum likelihood means to maximize, this expression over all the models. What you do. And of course, it's like you do it on the left side of the equation, you can do it on the right side of the equation. And if I'm maximizing over all the models, first thing that I can do is just to remove this expression, right? P of D. It's because it's the same for all the models, right? If I'm maximizing over all the models, I can delete it. That's it. So that's how easy math is, right? And that's called the prior. what's the prior probability of the model before seeing any data. And here, like very physical basic constraints can go in. For example, right, there's detailed balance and all these things. So very fundamental beliefs or very fundamental things about models go into this term. This then depends on the data. And for the specific case, it's also called the likelihood. I think this one. It's called the likelihood, if I'm not mistaken. And the likelihood for such a model, you can write it down like this. So let me explain to you why this looks like this. So here you just, it's a very similar form than the one that you should have seen in the MSN talk. In the MSN talk, there was an expression which was like a transition matrix taken to the power of the count matrix, if you remember this. So this looks very, very similar. So here it's a stationary probability taken to the power of number of counts. And the idea is exactly the same. So what you did in the Markov state models is the probability of seeing a certain sequence of events, like the probability of, for example, of seeing the transition 1, 2, 3, given the transition matrix is T12, T23, right? If there's something, let's say, right? For such a thing, right, you can just write it down. 2, 3, 2, 2. Right? So this is the probability of seeing the sequence 1, 2, 3, 2, 3, given the transition matrix. And the probability would be like this, right? Just multiply together all the transitions, the probability of seeing every single transition. And then you realize, oh, there's a term which is occurring twice, right? That's why you can use a count matrix. Where you can see, okay, that's P12, P23, to the power of 2, P2. Where this expression came from, of the transition matrix taken to the power of the counts. And here, it's exactly the same idea, except that you're not working with transitions, but we are seeing with realization, right? So we're working with like visits instead of transitions. So here you asked for the probability of observing the set just 1, 2, 1, 3. Well, that's pi 1, pi 2, pi 1, pi 3. This pi 1 takes the power of 2, pi 2 takes the power of 1, pi 3 taken to the power of 1. It's very similar idea, right? So the count, in this case it's a visit, number of visits, ends up in the exponent, and the probability is the base of this exponent. So this is why this expression takes this form. So there's two products, like the first product runs over I. So that's the assumption that these samples, that's the same product that I've written here out as dots. And as the underlying assumption is that like the samples that you have drawn from a single simulation are independent. It's questionable, right? And there's a second product which runs over K. And this you're saying, okay, all the simulations that have carried out, all the different umbrellas, they are independent, right? So for every umbrella that I've umbrella potentials that I've produced, I've run an independent ND simulation. So now I can model the realizations as being independent. So that's why I can just take the product of all the probabilities. And this gives you a likelihood now. And now this idea of maximum likelihood, one can optimize this expression over the values of pi. So what is known is n. This is the realizations that you get from the data, and you optimize by some stochastic optimizer or by a more clever trick over all choices of pi until you get the until this likelihood is maximized. Just to show this something like in a workflow style diagram, what we do is that we did have these bin definitions and counts. So these are input data, like NIK. And the second set of input data, which we should not forget about, is the bias potential values. So it's the bias that we have picked, really. So we picked our umbrella definitions. So we can, for every conformation X that we get from the MD simulations, we can calculate this bias. Or we know it from the MD software. And now this was our likelihood. So I've now inserted all the equations together. So that I've put more separately on the last slide. Just put everything into one big equation. And you see there's like different kinds of symbols, right? There's like red stuff and green and blue stuff. And this is known. So these bias factors are known. These counts are also known. Bin counts from the simulation. And the only unknown is the red quantity, which is pi I. But this is the one we're optimizing over, right? So you can take the derivative, for example, of this function with respect to pi and set it to 0. And for every pi, you get an equation, right? Derivative of L with respect to pi 1 is 0. Derivative of L with respect to pi 2 is 0. So we have as many equations as we have unknowns. So we can solve this maximization problem. And what we end up, after having carried out this optimization, is the stationary probability pi. That's how you get from realizations of bias simulations back to probabilities in the physical ensemble. Okay, so you can open this notebook on your computer as well, if you like. It's in the day 3 Trump folder, and I think that it's lectures, lecture, right? So we're here on day 3 Trump, and then it's lecture, US lecture. So US is umbrella sampling. Quite funny if you read for the first time. We think like very patriotic PNS papers and all this stuff, but it's actually umbrella sampling they're talking about. So this is more, it's very much more practical, this tutorial. So we have defined now, we're doing umbrella sampling. So maybe just skip down a little bit to the picture. It's actually the same example from the lecture. So we have like this double well potential. Here you see the corresponding probability distribution. And here is the energy landscape which produced this probability distribution. And what we're going to do, what is prepared in this notebook, is to add these umbrella potentials on top of this physical landscape and analyze the simulation data which came out from the simulation. So at this stage, we say, okay, the simulation has been done, and we have the data, and we now want to analyze the data with PyEMMA. So in order to analyze the data with PyEMMA, we have to define these bias functions. So right, on the WHAM slide, we have like NIK and dk of x and dk of j. So we have to input these two quantities. We have to produce these two quantities. And this looks, for the case of umbrella sampling, right, this is dk of x takes a specific form. So namely exactly this one, which is here in the tutorial. So the bias energy is a spring constant times a quadratic function centered at a certain location, xi. Right? So like an umbrella potential is it's characterized by two parameters: the rest position, where it's placed, and the steepness, which is given by the spring constant k. So we are going to read these rest positions and the spring constants from some file in this case, and we're going to read also the instantaneous location, so the simulation results of this order parameter into PyEMMA and give it to a specific function which is made for umbrella sampling. So there's like, if you type in PyEMMA.thermo and if you then go type dot, you will see different things. So among them is estimate umbrella sampling, which is like user-friendly wrapper made for the analysis of umbrella sampling simulations, and it takes the job of calculating this bias value for you. But you have to give like the definition of your umbrellas of the umbrella sampling simulations that you have made, and this definition consists of the spring constant and the rest positions. And if you look through the parameter list of this function, you'll see something which is called US threshes. So these are the umbrella sampling thresh. So it's the value of x for every point in time. So US threshes, these are like stuff which will help you to define your bidding. You will see this in a moment. And of course, like the definitions of the umbrella potentials, so the centers and the force constants. Okay, so let's run this. So here we have prepared, executing from the top. So here I'm just loading the data that I've already prepared in advance. In the afternoon session, you will see how to do this more like by yourself if you have run a GROMAX simulation, how to import this data. But here it's like already like present as a list of files. Let's look at the data format. So we have now a set of trajectories. So this is giving you the number of trajectories, and of course it should be equal. So like the number of umbrella sampling parameter trajectories should be the same as the centers and the force constants. So the layout is in this way, right? So for every simulation, for every trajectory, you give a time series of instantaneous values of your order parameter, and a value of the spring constant and the value of the umbrella center, right? So like that's the nature of umbrella sampling simulations, that you never change the umbrella sampling or the umbrella definition during the simulation. It's always the same. So for every simulation, so for every trajectory, there's one constant value of the spring constant, one constant value of the rest position. That's why these can have the same length here. Let's just skip this. So let's look at the format of a single umbrella sampling trajectories. Well, that's just a very long vector. Like this is now 1001. It's the number of time steps which are in this trajectory, and then it's one-dimensional because there's like only one order parameter in this example. We can do now a histogram of the order parameter in every simulation. Just draw them on top of each other. So it looks pretty much like on the slides, right? So there's like a different set of simulation. Every simulation samples from a narrow part along the order parameter, and altogether they cover the whole axis. So it looks like a nicely prepared example where you're sampling the whole x-axis together. Okay, so now we have to go through certain steps. And the first step involves calculating these bin counts. So it means we have to introduce something like a histogram, which means that we have to discretize the axis. And I mean, you should have seen discretization like during the first 2 days of the workshop. There's like in PyEMMA there's a standard function to do this discretization, and it's called cluster something, right? So in this case, I'm using PyEMMA coordinates cluster rect space. Could also be k-means or something else, just to discretize my x-axis. Okay. And like with this data set prepared in such a way, I'm almost done now. Now I can use like the PyEMMA thermal.estimate umbrella sampling function, and I have all the stuff that's already prepared. So I have the umbrella sampling trajectories that I had loaded from the files. I've now done this discretization, which goes into the second argument of this function, and where's the umbrella definitions, which are the remaining arguments. Then I select the estimator, in this case which is WHAM. We will see like in the remaining parts of the talk that this can be changed. So I'm running this estimator. And I can plot some information about the convergence. So I'm showing here in the second part the decrease of the log likelihood. So I said it's a likelihood optimization. So internally this routine should decrease the log likelihood.
It increases the log likelihood, but decreases the increments in the log likelihood.
The increments of the log likelihood. Yeah, that's correct. So it's converging, let's say that's converging, and now we can plot, in the end we can plot pi, right? So what you get from WHAM is just pi, so let's plot pi. So here now the dots, the squares, are the pi estimated by WHAM, and the black curves was the original reference that we know for the system. So we know, see it's pretty close, even though it's not perfect, it's pretty close. So this property, you get it on this object. So that's like a histogram estimator, this object. So you can also just press tab, right, and look through the properties that it has. And I think there's something like a station distribution, right, which is easiest to understand. For example, like this. And if you would plot this, you can actually try to plot this. Then this looks very weird. So why does it look so weird, right? That's because the states are shuffled, right? So here I'm plotting this value of pi over the index I. But the indexing of the Markov state is something arbitrary, right? So like the index I of a Markov state number I doesn't have to correspond to the location along the x-axis. That's why in the plot, which we have prepared here further down, we do a more complicated plot command where we plot like estimating double umbrella sampling x. So we have prepared like something like a mapping from the state indices to the x-axis. So that's also something you should keep in mind, right? That the indexing of a Markov state is usually something arbitrary. You have to first map it back to your reaction coordinates that you're interested in. Okay, so let's have a break.